Oh, hello, great lecture, by the way. So I did want to ask you, does the idea of a wormhole support the idea of an infinite universe? A universe that's just existed infinitely without the beginning of a Big Bang?
Okay. Oh, this is a good question. So I don't think it necessarily supports it, right? So it's true that if our universe had always existed and there had always been these wormholes in it, then you don't have this problem that I mentioned about needing to punch holes in it. Whereas you're right, I guess if you start with a Big Bang, okay, we also don't understand the Big Bang very well, but there's no obvious way that the Big Bang would form something that had these tunnels already built in. So I guess, yeah, if you have a Big Bang, maybe that makes it less likely to have wormholes, whereas if you have something that's already existed and it's already had these connections built into it, then yeah, maybe it's like, I guess you're starting to talk about more likely or less likely in areas where you kind of don't understand the physics very well.
Well, then what about the idea of multiple Big Bangs? Could have that affected the rips in space-time?
Multiple Big Bangs. Well, okay, so we need to be careful what we're saying about Big Bang. If you're talking about the singularity at the beginning of time, so this is where if you rewind the universe, everything comes back. But at this point, we don't really understand what's happening, right? At this point, you need a theory of quantum gravity to really understand what's being generated there. So we have this idea that is inflation, where you have this mess that's created from this singularity, and then it all gets blown up onto big scales and makes our universe very smooth. But even that idea, it's not been proved. It's consistent with the evidence we have, but it's not been proved. So I think, maybe when you say multiple Big Bangs, you have this idea of a bouncing universe where you have multiple bounces, the universe expands and then contracts and goes through multiple phases. As I say, I mean, these are all theories which do not yet have scientific support.
This is a bit of a trivia one. Do you watch The Big Bang Theory?
I do, actually. I do. I quite like it. So I haven't watched all of the series, but yeah, it's kind of embarrassing how accurate it is sometimes, right? I mean, you definitely know people who are like that. You also know a lot of people who are not like that, to be fair. Some people are normal. I hope I come across as being reasonably normal, apart from my hobby of warp drive simulations. But yes, I do, yeah.
Thank you very much for the talk. It was really, here on the right. Hello.
There you are.
I have, two questions within one. You mentioned wormholes within our universe, but what if it was between, let's say, if there were in higher dimensions, if they were to exist, and also between 2 or 3 different universes?
This is actually a really good point. Yeah, so I didn't mention this, and I actually was going to. So you can solve all of these problems if you just don't have them connecting the same universe. If you're going to a different universe, you can never do this thing that I described of like bringing them together. So you're never going to create these closed time-like curves, these things that violate, allow you to time travel. So that's a really good point, and that would be consistent then with what we know. You still have this problem of needing exotic matter to be able to make a tunnel that you can actually go through. But in terms of this causality argument, that kind of solves it. Yeah.
Hello.
I'm not very good at seeing where people are.
On the right.
You have to.
Over here.
You have to wave. Okay.
Hello. So do black holes spin? And if they do, on the picture of a black hole that you showed us, where is the axis of rotation? Because I don't quite understand why the middle is black and the edges are all bright. Because if it were spinning, I would imagine I could understand one edge being bright and the other one not. And if we're looking at the black hole and it's glowing all around it, why do we not see it glowing all the way? Where do you think the axis of spin is on that picture?
So in this, we're actually looking more from the top. So I think it's easiest with this one. So with this one, the idea is that the axis of spin is like this. And so this is the accretion disk. This is like a disk of the gas around the black hole. And so the reason it's at the top and the bottom is not because there is stuff at the top and the bottom. It's because the light from the stuff gets curved around the black hole. So it kind of looks like it's this sort of ring of stuff around it this way, but actually it's just in this plane, it's just in this ring. And as I say, the light from it is being kind of bent by this curvature of space-time. But your question is interesting. So I guess you're asking, like, how do you see the spin in this image? And I'm not sure that you really can see it. So the thing about the spin of the black hole, so saying black hole spin is quite interesting. So really the space-time is curved in such a way that when the black hole, so what we call the black hole spinning is really that it causes things around it to have to move. So it's almost, sometimes I think of it like being a helter-skelter, that you know, somehow you have to keep like going round and round the black hole. You can't go to the black hole and then just kind of sit there. You have to be carried along with this curvature. But as I say, I don't think you can actually really see the spin of this black hole in this image. But generally, the accretion disk would be aligned with the black hole spin.
Hello.
I was wondering, I've heard that dark energy is making the universe expand. So I was wondering if dark energy pushes things away from each other. Could some civilization in the far future that can harness dark energy use that on a warp ship to stop the waves or like crushing the ship? Could they use dark energy to repel them and not get crushed?
Yeah, that's a really good question. So dark energy, yeah. So for people that don't know, dark energy is a component of our universe that we really don't understand very well, and it is primarily responsible for this expansion, but not only this expansion, the fact that we're expanding, but the fact that the expansion is accelerating. So I talked about how galaxies were moving apart over time. That's actually getting faster, right? So it's getting faster over time, and the fact that it's getting faster tells us that we have this component of dark energy. So yeah, dark energy, as I say, we really don't understand it. It's very, very dilute. So the amount of dark energy in this room is just infinitesimally small. So it only really affects things on very, very large scales. So, but I think it's still a great idea. So it's definitely not sufficient dark energy to build a warp drive, because you need, as I say, negative energy. And so actually dark energy has negative pressure, but not negative energy. So it's not enough to build a warp drive. But I like the idea of using it to somehow protect the ship. I think that's a nice idea. So yeah, why not? You can, if I can build a warp drive, I can do anything, right? So.
Thank you for your talk. I really enjoyed it. I liked your idea using the rubber mat demonstration for why intergalactic space is expanding, and looking at the way that a black hole forms a region where you cannot escape. The opposite of that potentially is a region that you can never get to because you can't overcome the space-time gradient, which is quite interesting. And then could that not be the other end of your wormhole, a one-way wormhole?
Yeah, so this is an idea called a white hole. I don't know if you've heard of it. Yeah, so white holes are another. So I thought about talking about white holes, and I decided that 3 was probably enough objects for one evening. But yeah, there's a possible solution to the Einstein equations, which is to have a white hole, which is really the opposite of a black hole. So it is like, maybe if I had my sheet, I would have like pulled it up like this, like grabbed a bit and pulled it up, and then everything would have to sort of fall away from it. So it's like it's the opposite of a black hole in the sense that you can't fly into it. It's like, everything that's at the top has to come out. So the difficulty with white holes is it's what's called a naked singularity. at the center of a black hole, like we don't know what's there, right? Everything becomes very dense, and suddenly you're into this regime where you need quantum physics to explain what's going on. And in every point where that happens, as far as we know, it's surrounded by an event horizon. So it's like nature kind of covers up these parts of the universe that do things that we kind of don't know what they should do. It's kind of frustrating in a way, because this is exactly the type of, like, the part of space that we would like to go in and see. And there's always just naturally arises this event horizon around it. So it's called the cosmic censorship conjecture. It's another fancy conjecture. So you notice that it's a conjecture, right? Like, it's not been proven. So there are some counterexamples, but they're very sort of tuned. They're very difficult to achieve. But a white hole would be a counterexample to this. It would be something where this singularity, where quantum effects happen, is visible, because anything that happened there would inevitably come out of this white hole and we would see it. So for that reason, as I say, people don't think that white holes exist, because they would, as I say, they would somehow put out stuff into the universe from some, as I say, quantum singularity that we couldn't predict what came out of it. And so somehow that would pollute the predictivity of our universe, the fact that we can predict what happens next, the causality of our universe. But yeah, in a sense, they're like sort of wormholes and warp drives in that they are good solutions to the Einstein equation. In principle, you could have them, but they cause lots of problems for other areas of physics.
Let's get to the balcony.
So, approaching it from a bit more of a mathematical point of view, how topologically different is just a flat plane or slightly curved plane from a wormhole? And how is there an actual way to modify the topology of the plane?
Yeah, exactly. So actually, I didn't use the word topology, but this is exactly what I was getting at when I said about like punching holes and sticking things together. So a flat sheet is somehow different topology. So this word topology means sort of, can you smoothly deform one surface into another? So if I have a sheet, I can bend it. I can somehow sort of bend it to make a different sheet. But if I want to make a wormhole, I had to bend it, and then I had to cut and stick bits of it. And this cutting and sticking is changing the topology of the surface. And so the reason that is not allowed is, well, actually it's been proven mathematically that if you want to have a universe that's causal, that doesn't have these closed time-like curves, you can't have something where the topology changes of the universe. You can't have it going from being a smooth sheet to one that has, holes cut in it and stuck together. That's forbidden.
Hi, thanks for the talk. I'm here, black and white sweater. So a couple of years ago, there was news that a couple of scientists essentially simulated a wormhole inside one of Google's quantum computers and sent an electron through it. Now, I understand it's a simulation, but I would like to know from you how useful that kind of an experiment is and what's happening there.
That's a really good question, and I don't know how to answer it because I don't really know the details, but I just remember everyone being really annoyed about the way that it was publicized in the newspapers, like simulated a wormhole. So I think they were simulating a wormhole in the same way as I was simulating a warp drive. Like, I didn't make a warp drive, right? I didn't really have one. I just, did a computer program that looked like it would look. And so I believe that was the same with this simulation of a wormhole in this quantum computing, that they were just kind of making something that somehow behaved like a wormhole would behave. So it wasn't really kind of creating a wormhole. But yeah, as I say, I only just remember the sort of the controversy of people saying, this is not how it should have been publicized. But, okay.
Over here, to your right. Okay. So the reason why the material in the demonstration was bending was because of the weight of the balls. So why do stars bend space-time? And why does it kind of go downwards?
Yeah, so this is the sort of the flaw in this demonstration of bending the stuff. Because in a sense, gravity is what's bending the space-time. So it is, as I say, it is kind of schematic. So it's easier for that reason, I think, to use the other analogy that I gave, where you're moving on the surface of the Earth. So then it's really not that you're being kind of pulled down. You're not, like the Earth is just a curved surface. It has a certain curvature. And then when you move on it, you are forced to follow the contours of that surface, right? You have to move on the curved surface. And then that's what makes you come together or move apart. So that's why, in a way, I like that analogy better than the stretchy sheet one. But I think the stretchy sheet one is nice because it does give you this idea that what is curving, what is creating the curvature, like the curved surface of the Earth, is the stuff in the space-time. But I agree, it's not a perfect analogy. It somehow incorporates gravity into it in a way that you wouldn't really want.
Yeah, over here. So I was just wondering, after you answered the question earlier about how it would be you could make a wormhole hypothetically with a hypothetical different universe, would you be violating anything if you popped into the other one and then came back out, went in and then still came back out into ours? Would that be theoretically? I mean, it's kind of wild, but...
So you want to go out of the wormhole into the other universe?
Yeah.
And then come back again?
Yeah, would you be violating anything if you did that?
Yeah, so as long as it was the same wormhole, you'd be all right. So the problem you get is if there's two, so two wormholes both connecting different universes, then you can like do a loop, right? And then that's a bit like the one wormhole connecting the same universe, then that's problematic. So as long as you've only got one wormhole connecting you to another universe, yeah, you can go through and that's all fine. Like you can go through and come back. You can definitely do that.
You can't take a shortcut in our universe by going into a different one. That's the same.
Yeah, so then, as I say, then you need a second wormhole, right? So you need to be able to go through this one, travel along and like come through another tunnel to come back to our one. And then that's problematic. Yeah.
So you're then basically still cheating, right? I'm just curious. Thank you.
Okay, let's go to the balcony.
Hi, so I was just wondering, with the photo of the black hole, like the one from the Event Horizon Telescope, that kind of seems like the gases are concentrated in 3 places, making like a triangle. Why is that?
Yes, so there were lots of questions actually about this when they made their press announcement. So there were questions about whether it's an artifact of the image. Actually, it's not one camera that takes a photo. It's actually lots of radio telescopes that combine their data. And, they were asking, could this be somehow correlated with the pattern of where the telescopes are? So they certainly said, don't take these 3 blobs too seriously. Like these 3, this is a kind of, this is a kind of approximate image, and you shouldn't think that, this is the sort of the final answer. It was, as I say, it's actually created in quite a complicated way. It's really worth kind of Googling if you have time, how they put this image together. They actually generate lots of different images, and then they kind of combine them into their most likely image of what the black hole looks like, and this is what they get. But yeah, the message that we got is you shouldn't read anything too much into these 3 blobs. It could be something of an artifact from the way that they take the image. It could just be a kind of a coincidence in the way that the angle of the gas or the way they took the photo. But yeah, it's a really good question. It's actually, as I say, one that came up in the press conference when they had this image.
Hello, hi, here. If massive stars can become black holes, do black holes ever become anything else? And if they don't, are there any implications of there being more and more black holes in the universe?
Yeah, that's a really good question. So black holes are, in principle, the endpoint, but actually what was shown by Stephen Hawking is that they can evaporate over time. So there's a kind of a quantum effect that happens near the horizon that means that very slowly they can lose mass. And so they stay as a black hole, but they just gradually kind of get smaller and smaller and smaller until they go poof and there's nothing left. But that process takes an enormous amount of time. I mean, so much longer than the age of our universe or the age that we've already had for one that's formed from something like the sun. So, if our universe is still around at that time, eventually the end point will be all of these black holes going sort of pop, in different parts of the universe. And so everything will end up just being, so radiation, so like photons, so light, is what they evaporate into. So that's the end point of the black holes.
Okay, we have 3 minutes. I'm going to try to do 3 questions in 3 minutes. So
Hello, thank you. I've seen previously a pie chart showing a distribution of masses, like something like 5% the normal mass, matter, sorry, 25% dark matter, and then the 70% remaining dark energy. You showed us here a model where the expansion of time, or the curvature of time, rather, is responsible for the expansion of the universe. But we've also heard that dark energy is, or might be, responsible for the expansion of the universe. If we have this model of curvature of time, do we really need dark matter, dark energy?
Yeah, absolutely. So this curvature of time that I was talking about, the fact that time is curved, the question is, what is curving time? And the thing that's curving time is the dark energy. So it was like my ball that I'm putting on the sheet. The ball here is dark energy, right? This is what's causing the time to become curved in this way that makes, as I say, things move outwards.
Hi there. It was kind of related to what the gentleman has just said, but my question was, I suppose, when you think about the way that mass sort of deforms space-time, and then the converse about how it explains the sort of expansion of the universe, do you think that the middle's being pushed up or the sides being pulled down? And I suppose, based on that shape, if you see the way that mass deforms space-time, that kind of gives you clues as to how that the inverse square law kind of implies that. Does that give you any clues as to how, the equations of how that might work?
Yeah. So yeah, it does. Yeah, this is exactly actually what I find really fascinating, is this idea that we can somehow use this, what we can measure about the curvature, to maybe infer something about our universe, I don't know, on bigger scales or at earlier times. So one thing that's really interesting, which is a bit related to what you're saying, is that actually the universe could have been curved in 2 ways by the matter that's in it. It could be curved such that things move outwards on large scales, or it could actually have been curved such that things collapse. And we're kind of lucky that we happen to live in the universe where it's picked to go in the direction of expansion, because if it was collapsing, we'd all collapse into a point and we'd all be crushed. So using this idea of how things are moving and how curved, tracing it backwards through our history of our universe, that's exactly what cosmologists do to try and infer things like dark energy and dark matter. That's exactly how we work out that those are components of our universe. And we hope that we can kind of rewind things backwards to the beginning, but once we get to the beginning, everything becomes a bit confused and it's not clear exactly how we can make the picture work anymore. So yeah, I think that whole idea is exactly, cosmology and gravitational physics. Yeah.
So do you think pulled up in the middle or pulled down?
Oh, I see. I avoided the question. So really you're asking about, is the universe a ball on large scales? And so from what we can see, it's actually at the boundary between being a ball and being a Pringle, if you can imagine Pringles. People used to say saddles, but no one rides horse. Well, I don't ride. Maybe people do ride horse at the Queen. Anyway, people, don't say saddle anymore. They say Pringle, because everyone eats Pringles. So our universe is actually exactly balanced between these 2 shapes in the sort of the spatial thing, and it's sort of flat, which means it would kind of go off to infinity in some way.
I'm going to take one last question, and that's on the balcony.
Hi. So I was wondering, if a black hole can almost make you go forward in the future, can a white hole make you go back in the future? To past.
Quite nice to finish on the Back to the Future stuff.
Back to the Future. That's a really good question. Would time somehow flow? I don't think so. No, I don't think that you get closed time-like curves from white holes. I don't think so, but it's a good question. I'm going to go and work it out later.